Hello, everybody. Welcome. We're going to be talking about space applications today with a purpose of solving fluids type applications in space. This is the fluids product set here. So you can see when we say Ansys CFD, we actually refer to a number of specialist products. So over on the left, we've got the Fluent and CFX CFD solvers. So these are general purpose solvers, which you can apply to a multitude of different types of analysis. Then in the middle here, we have some specialist solvers. So things like ChemKim Pro, that's specifically designed for chemical reactions, combustion, fuels, and so forth. Moving along, we have materials processing. So that's really manufacture in the form of polyflow, icing, aerospace icing, FENSAP ice, particulate simulation. And over here, we have thermal desktop, which is coupling different solver physics for thermal applications. We're going to focus primarily on the general purpose CFD side, though. One of the most interesting applications that's relevant to space is it's actually fuel sloshing. And there's a number of things that CFD can do to assist in the design process here. So it may be looking at flow through valves, it may be looking at evaporation, condensation in tanks, filling, sloshing, emptying, and also fluid structure interaction. So this is where we can use the CFD solver to very accurately simulate the movement of a fuel in a tank. And then we can use those pressures and forces to map across to a structural solver, which can then look at the stress and material implications of the movement of that fuel. So we'll look at propellant management device tanks and a couple of simple applications. So why would we need to do this? Well, if we have fuel sloshing, even on a ground-based application, if you think about your car when you're braking or a tanker truck, it's got a large mass of fluid inside it. Movements of that fuel can create huge forces. So it's very, very important that that's considered during the design process, because that has massive implications on stability and so forth, and can cause all kinds of problems there. It's traditionally been accomplished by, there's various analytical methods. So, for example, sloshing motion during flight conditions, there's methods such as pendulum or spring mass systems, which can go so far, but they have their limitations. Really, the only way to get as close as possible to the movement of a fuel inside a tank is to use a CFD analysis. So CFD using Ansys Fluent, that can provide that insight. All we need to do is to provide the representative operating conditions. Once you've done that, then you can get the entire operating cycle of a propellant tank, all of the forces, pressures, and so forth. And that's just going to lead to a better tank design. So generally, rockets powered by liquid fuel, which is generally stored in a pressurized tank. That then is subject to gravity forces and inertial forces as the rocket is under motion. So normally we'd have pressurization with an inert gas inside the tank, and as the fuel is getting depleted, then that's accompanied by movement of the fuel or sloshing, which causes forces onto the tanks. There's also the possibility of getting aeration. Some of the gas can get entrained into the liquid in the form of bubbles, which can then get into the engine ducts and into the engine. So things that we want to avoid. Primarily then, we do this to promote stability. We want to promote continuous uninterrupted delivery of fuel to the engine and eliminate the possibility of any kind of engine malfunction due to gas bubbles getting entrained into the engine itself. So this is a simple case study here, which we've been completed using Ansys Fluent. So we've got a capsule tank over here, and you can see we've got the computational mesh there, and this is the fill level. So 50% filled with liquid, and this tank is actually a drop test. The data that we used is available from NASA there, and the simulation runs the experience of the tank according to the motion profile, and we can see how that fluid moves in accordance with the forces acting on it. So these are typical motion profiles that we'd use as an input into Ansys CFD. So we've got the Z and the X profiles here, which give us the acceleration that the tank is subject to. So this ramps up for just 0.08 seconds. The simulation time is just over 1.5 seconds. Now, when we run the simulation, this is what we get from Ansys Fluent. So the coloration here, this is actually a scale from 0 to 1, which represents a volume fraction of the fluid. So where it's red here, that's meaning that it's 100% fuel. The blue is the gas. Now, what it can do, what it can output at each time step is the precise position of the fuel as the tank is subjected to those external loads. So you can see that compared to any analytical method, the CFD is able to give us a very, very accurate understanding of what's actually happening to the fuel as the tank is subject to the loads that it would be under operation. So you can see the interface between the fuel and the air is very accurately captured. Now, having this information then gives you a much better chance of designing mitigation methods that can either control the motion of the fuel, or at least give you an understanding of how that motion is going to create potentially other problems, such as the forces as it's impacting the side of the tank and any possible air entrainment. So typically then, these are the results that we get out of this CFD simulation. So I've got the force over time of the 1.6 seconds that this was run. Another example using a similar tank here. So again, it's capsule tank. This simulation using CFD replicates the launch conditions of the tank. So again, we've got a tank which is initially full or filled with liquid fuel, pressurized, and we've got helium flowing into the tank from the inlet. As the launch process goes through, that fuel is obviously depleted, and also the tank is subject to external accelerations. So typically then, this is the input profile that we have here. So acceleration in terms of horizontal acceleration and vertical. So the horizontal acceleration there is giving us the sloshing, and this simulation is run for the first 250 seconds of the mission. And this is just a typical representation of the tank trajectory as it's being launched. So I've got an animation here, which I'm going to show you. This has been completed by Ansys. So you can see that the CFD is able to give us both the depletion of the fuel and the motion of the fuel as the vehicle goes through its launch process. So we can see here the fuel mass is decreasing. And as the vehicle changes its orientation, you can see the impact of the accelerations on the fuel itself. Okay, and hopefully from this animation, you can see that level of detail is far beyond anything that you could get from more of a simple analytical method. So using CFD in this way gives you data that is as close as possible to the real experience of the fuel sloshing during a launch procedure. Okay, so that was the first example I wanted to show you. So we've shown how CFD can give you information that helps you understand the stability, helps you understand any potential entrainment of air bubbles and so forth. And with that information, then you can design either the product itself or make adjustments to the mission to mitigate any of those issues. Another example that I'd like to look at here is this is more of an aerospace example. So we're looking at the actual launch, separation, deployment, and impact and recovery. So this is where this is quite a traditional application of CFD in the aerospace world. So we're looking at atmospheric impacts here. CFD lends itself very well to external aerodynamics. So essentially simulating the airflow over an object, and at high speeds we have to think about things like viscous heating and so forth. Another factor to this is that we can use CFD in conjunction with another physics solver. So for example, mechanical. And here we have a nice application of fluid structure interaction on an external bluff body. So what we're doing here is we're running the CFD simulation to give us the pressure and force data, and then we're passing that over to a structural simulation using Ansys mechanical. And this can happen, it can be a one-way transfer. So for example, where aeroelasticity is quite minimal, or where you have large deformations, you can do a two-way analysis where data is passed back and forth between the two solvers. So as you can see here, where we have large deformations, then this would be a 2D, a two-way FSI analysis. The operating environment in Ansys makes this really, really easy. You can just drag and drop different analyses onto each other, and they will just pass the data between them. So just in general then, multiphysics, that's an example of fluid structure interaction, but you can also combine electronics, you can exchange data between any one of these three solvers. And that's increasingly important because not just in space applications, but anywhere, you have to consider the coupling between physics. So back to our little case study then. The sounding rocket through the atmosphere here. We've got our input profiles here, so Mach number, altitude, angle of attack, temperature, pressure. We're conducting a CFD analysis to get the external aerodynamics forces that are occurring here, and we're combining that with a structural analysis to look at the thermal effects of the materials in the actual craft. So typical results then from this type of analysis here, first of all looking at the external airflow here. So we've got our Mach number contours at different times from 0 to 30 seconds. We've got our external fluid temperature contours here, again from 0 to 30 seconds at different parts of the operating cycle. And then we can start to look at the thermal structural side. So start to look at wall temperatures and internal component temperatures. Okay, so that's on this slide. This is the Ansys mechanical analysis. So this is conducting a thermal analysis of the internal components based upon data that it's received from the CFD analysis. So a nice simple example of how you can use CFD and combine that with structural thermal mechanics. So we use this to simulate a transient re-entry and look at aerothermal behavior. And essentially we're using what we call system coupling or multiphysics, and that's used a number of data transfers. So we're transferring near wall temperature from the Fluent CFD solver to mechanical, a heat transfer coefficient from the Ansys CFD Fluent solver again to mechanical, and then we're taking wall temperature back from mechanical to Fluent. But that's just one example of multiphysics. Again, you can include structural deformation. You can also include electronics solvers as well. Okay, the options for that kind of analysis are either steady, so where you have a steady frame of reference, or fully transient. So if you think back to that deforming bluff body that I showed you, that would be a fully transient two-way FSI. Depending on the precise circumstances, you might be able to simplify that and have a one-way FSI. The difference is essentially compute time, but either one of these methods is available and made easy for you to do. Okay, so I'd like to conclude the presentation here, and thank you for your attention. And hopefully you've seen some examples here which are interesting, and if you do require any further information on anything that you've seen today, we would be more than happy to open a discussion with you.